Welcome back from lunch. This morning we heard from Max and Nate about the next feature they're going to implement within Python GitLab, GraphQL support. Now we have Andy Roberts from Apollo GraphQL giving us some more insights on GraphQL and the open source tooling around.
Hi everyone, and welcome to my talk about empowering GraphQL at scale with Apollo open source tooling. My name's Andy Roberts, and I'm the Senior Manager for EMEA Customer Success here at Apollo. In today's talk, we'll be covering Apollo's open source journey from its prehistory, before Apollo and GraphQL even existed, when the team was focused on building out Meteor.js, to the fortuitous timing of Facebook open sourcing GraphQL at just the moment that the Meteor team were looking to abstract away underlying data sources, and how the rapid adoption of the Apollo open source offerings, Apollo Client and Apollo Server, quickly established Apollo as the thought leaders in the GraphQL space, leading to the realization that organizations needed a way of pulling together their disparate graphs and APIs into a cohesive whole, leading to the birth of Apollo Federation, and ending with the creation of a commercial offering that empowers organizations to deliver GraphQL at scale while still providing the open source tools that developers need and use in their everyday workflows. Along the way, I'll give a brief introduction to GraphQL and how it works for those who are unfamiliar with it, an introduction to the concept of the graph and the problems a unified data graph solves within modern product development, followed by an overview of Federation and how it helps to build out a unified graph. So, in the beginning, there was nothingness. Well, hang on, let's not go that far back. Let's fast forward instead to 2011, when a new platform was spun out of a Y Combinator startup. A preview of this platform was released with the name Skybreak, but it was rebranded a few weeks later to Meteor in January 2012. Meteor was and is an open source framework for building full stack JavaScript applications from the clients to servers and onto the underlying databases. It offered an opinionated way to build JavaScript applications, presenting developers with a carefully curated set of packages wrapped up in a developer-friendly API. Open source was at the heart of Meteor, and the entire framework was available to everyone. It generated a lot of buzz in the JavaScript community at the time, and its popularity generated a large and very involved community that helped contribute to the project and the wider ecosystem. This community has stood the test of time, and today, 10 years on, Meteor still has a vibrant community and nearly 43,000 stars on GitHub. The plan was to capitalize on this community and the mass adoption of Meteor by offering a platform as a service, Galaxy, that allowed Meteor developers to deploy self-contained Meteor apps onto Galaxy and not have to worry about any of the infrastructure needed to run it. Whilst Galaxy met with initial success, there was one big stumbling block. Despite developers loving Meteor, enterprises and larger organizations weren't adopting it. This was down to one of the big assumptions made about how apps should be developed: MongoDB. Meteor had always used Mongo as its database, but larger organizations either didn't want to use it or couldn't migrate all the data to it, and thus wanted Meteor to support multiple databases. Fortunately, through the power of the internet, we can have a sneak look back in time at the pivotal moment in the future of both Meteor and the yet-to-exist Apollo. Here we have the old Meteor Trello board from 2016. On it, somewhere is a ticket that changed the direction of Meteor and ultimately saw the birth of Apollo. If you look around, you can see a bunch of things that have been added, like supporting ES 2015, or improving the release process, and a bunch of future items such as adding a new API for UI components and full-text search. You may have spotted the ticket for additional database support, and you might be thinking, aha, that's the one, and you'd be close. But the one you want is just above that, the innocuously titled SQL support. This ticket may not look like much, but it started a chain of events that was to reshape Meteor and future adoption of GraphQL, but I'm getting ahead of myself. The initial intent was to add support to Meteor for SQL to garner wider adoption of Meteor, especially amongst the larger enterprise organizations. As the intention was to add more than just SQL in the long run, the Meteor team wanted to create an abstraction layer that clients could talk to without having to worry about if they were connected to Mongo or Postgres or Oracle or anything else. Several months before this, Facebook had released a new promising new open spec that seemed to be the perfect match for what Meteor wanted: GraphQL. This would provide a simple querying language that could be hooked up to multiple data sources behind the scenes, completely invisible to consuming clients. At the same time, there was an internal drive to make Meteor more incrementally adoptable. Historically, you either went all in on Meteor or not at all. There was a desire to change this and allow, say, the back end to be launched on Meteor and front end to be built elsewhere, or vice versa. To accommodate this, two new packages were created, Apollo Client and Apollo Server. Apollo Client was a new client-side GraphQL client that handled communication with a GraphQL endpoint and the complexities of managing a localized cache of data, whereas Apollo Server started to build out some tooling and developer-friendly APIs around Facebook's reference implementation of GraphQL, GraphQL.js. Initial excitement snowballed as both the Meteor community and the wider front-end development community saw the huge potential of GraphQL to solve some of the pain points that they had been feeling for years when consuming APIs. Both the Apollo packages' popularity continued to grow, and before long they were more popular than Meteor itself. So what is this GraphQL thing and why was it so popular? To start to answer this, I'll give a brief overview of GraphQL, which will hopefully show why the two packages became so popular so quickly, but we'll need a bit more of our story before I can show you the full power of the graph. If you're completely new to GraphQL, here's a little background. It was invented in 2012 by Facebook to solve a problem Facebook had when they were first developing their mobile app. They discovered that to build their newsfeed, they needed to make hundreds of service calls, and this was causing their mobile app to slow down horrendously. They needed to reduce the number of calls they were making and to reduce the amount of wasted data being sent back to their app. GraphQL allowed them to replace these multiple calls with a single flexible call that only fetched the data that was needed and nothing else. So what is GraphQL? Well, the GraphQL Foundation page at graphql.org describes GraphQL as a query language for your API. That's a pretty high-level description. The spec basically outlines a query language and the way in which a server should respond to query requests. I'm hoping by the end of this talk you'll be excited about GraphQL as I am, and as it offers us a way to build truly client-focused APIs that have an elegant story with regards to API evolution. So let's have a quick look at a GraphQL query. Here we have a simple query requesting a user's favorite products. Hopefully the query is pretty self-explanatory and it's fairly easy to figure out what is being requested. In this case, it's the ID of the viewer and a collection of products returned in descending order, with each having the product name, price, and any ratings that have been left as reviews. As queries in GraphQL are in this JSON-like request format, although note the lack of commas. Consumers of your API can pick and choose which fields to request based on the schema exposed by your GraphQL server. It's then the server's job to process the query and return data in the correct format and structure. Here's an example of such a response. As you can see, the data is returned in a shape that mirrors what was requested in the query. This predictable response makes it very easy for consumers of your graphs to reason with. The really amazing part is that the client doesn't have to care or even know where the data originated from the backend. Taking our example, it's likely that the data used to populate the response originated from various microservices, but you'd never know it when you were interacting with the GraphQL API. But of course, we don't want clients to be able to request absolutely anything from our API. For every GraphQL API, there is a contract in place that lays out the guidelines of what's possible, and that contract is known as the schema. In the example on screen, we see a schema written in what is known as Schema Definition Language, or SDL. In it, we define a number of types that are available for our clients to request, and within each is a number of fields, each with a type such as string or int. It is then the job of resolver functions in your GraphQL server to fetch the data requested in any incoming queries. The data can be fetched from whatever source you want, whether it be a backend database, an internal microservice, or third-party API. Historically, a lot of this data orchestration happened in client apps, but GraphQL and more specifically the resolver functions allow this to be lifted out of the client apps and moved into your GraphQL server. This leads to huge productivity gains for client developers and performance improvements for client applications. It also means that your client applications only need to know about one endpoint, not several, making ongoing development of your API simpler and more easily deployable. And that's it. Well, almost. There's a bit more to GraphQL than I just ran through, with the likes of mutations, an operation type that modifies data, directives, scalars, and a whole bunch of other stuff. But at its heart, it's a fairly simple spec. Most of the complexity of GraphQL comes with scale, and that's not something unique to GraphQL. It affects virtually everything we do as engineers. So with that in mind, let's move on to the challenge of running GraphQL at scale. I'm not talking about handling a lot of traffic through a single GraphQL instance here, more how to take advantage of a singular GraphQL API running across a large enterprise-sized organization. These often have dozens, if not hundreds of services that you might want to place behind your GraphQL API. Fortunately, another Apollo open source innovation provides a solution to this. But first, let's get back to our history lesson. With the continued growth and adoption of Apollo's open source packages and their use within Meteor, Meteor found themselves in a unique position where organizations were reaching out and asking for help with their GraphQL strategies and implementations. This led to a number of things, including the development of a collection of open source GraphQL tools to support teams building out their GraphQL services, and the creation of a tracing protocol for tracking performance of a GraphQL API. This work on tracing ultimately turned into a SaaS called Apollo Optics that offered insights into how a graph was performing and was the earliest incarnation of Apollo's main SaaS offering today, Apollo Studio. But it is the early work on schema stitching that proved to be the catalyst for the biggest change. Companies were telling Apollo that they wanted a way to merge together multiple GraphQL APIs into a single one to get all the benefits of a single unified API. Schema stitching used imperative code inside a gateway to stitch together the various other GraphQL APIs into a single combined API. This worked to a certain extent, but it definitely wasn't the easiest thing to build, run, or maintain, as all of the stitched schemas were tightly coupled. Internally, Apollo kept working on the problem and came up with a completely different approach, Apollo Federation. Released in May 2019, Federation is an open spec that uses spec-compliant GraphQL to extend the capabilities of GraphQL. Open source and free to anyone, it has been integrated into countless other open source frameworks, giving developers a rich choice of solutions to choose from. Apollo Federation is Apollo's answer to building a unified GraphQL API in a microservices architecture. It takes a declarative approach to composing a unified API, encouraging teams to split the schema up into concerns rather than types, therefore more closely aligning with how larger organizations tend to structure their development teams. But before we dig into Federation in more detail, I think it's important that we understand the problem that GraphQL and Federation is trying to solve. On screen, you'll see some of the world's most well-known brands: Netflix, Adobe, PayPal, Booking.com, Walmart, Audi, and even my previous employer, RS & Components. From retail to fintech, media to travel, nearly every vertical is represented, each with its own history, challenges, and competition, and yet they all share something. What is it? Well, that's the graph. All of these companies, and many more like them, have chosen to make the graph the foundation of their digital product development strategy. But what's driving all this adoption? What wasn't working with the status quo? Well, all these companies, unlike yours, are faced with three daunting challenges when it comes to delivering great digital products at speed. The complexity of an ever-growing set of devices and channels, all demanding a cohesive and coordinated customer experience, multiplied by the explosion of new services, and then multiplied again by the ever-increasing competitive pressure and delivery expectations, lead to a complexity bottleneck within organizations. With the move to microservices architectures, when the client layer consumes the microservices directly, the complexity of orchestrating all those services becomes their problem and yours. Integrating with all those services means adding tons of boilerplate code, and our customers tell us that up to 2/3 of their client teams' time is spent doing work other than creating great user experiences. Orchestration at the client layer also ensures features, behavior, and experiences will not be cohesive across the devices. And there are operational concerns as well. So what have tech leaders done to try and address this challenge? Well, API gateways were introduced to address operational concerns, yet they do nothing to address the complexity that client apps are facing. BFFs, or backends for front ends, were introduced by product teams to provide a simpler API that was tuned for their needs, but they quickly became duplicated and fragmented and are their own source of complexity. The REST API paradigm is simply not flexible enough to create a multi-client supporting API that can evolve as needed. Without a single source of truth, experiences stay fragmented, complexity still reigns, and delivery slows. This complexity bottleneck leads to a number of negative consequences for your product development. It acts as a productivity killer, with development teams wasting 2/3 of the time on API integrations that become increasingly complex as time goes by. That means productivity declines every year, backlogs grow, and deadlines encroach as frustration with delayed deliveries rise. It leads to fragmented customer experiences with high levels of duplication of effort that require expensive and time-consuming alignment to reduce. And there is an ever-increasing pile of tech debt that slows progress on any replatforming and makes any future innovation harder to commit to. So the combined effect of this complexity bottleneck is stifled innovation and frustration, both in your development teams and in the wider business, as more time is spent managing the complexity than anything else. But the good news is that there is a solution. An ever-growing number of companies are adopting GraphQL to solve their complexity bottlenecks, and this adoption is accelerating, as shown in the chart from the State of JS survey. What's better is they aren't just using GraphQL as a short-term fix or patch to get around problems, they're using it strategically. By introducing a new and essential part of the modern tech stack, the unified graph. The graph is much more than a better REST, and even more than GraphQL. It is an essential layer of your tech stack and tech strategy that connects client apps through the service layer, capturing your essential and durable business capabilities and exposing them all to your applications without tightly coupling your teams like point-to-point APIs do. The graph gives you an API built for building products that frees up your client dev teams to work on your product experiences instead of worrying about orchestrating a dozen or more interconnected service calls. It provides a query language that allows each app to pick the data they need from a shared contract that improves performance and removes complexity from said apps. The graph becomes a unified representation of your services, data, and digital capabilities in a declarative contract that is discoverable and flexible. It also acts as an insulating layer for service teams that allow them to focus on optimizing capabilities and architecture without the fear of introducing breaking changes. Historically, there has been a disconnect between app and service teams, with app teams having to massage the data returned from multiple services into something that makes sense for app development. Service teams, on the other hand, tend to only think about the data their service is returning in the context of their service, and not how this combines with dozens of other services. The graph drives collaboration between app and service teams, with them combining their usage and domain expertise to create a schema design that is the best balance between app needs and service realities. This upfront collaboration creates product-centric contracts that align with app concerns and acknowledge service realities, with iteration replacing perfectionism and version complexity. The impact of all this is an increase in product velocity as teams are freed from service complexity, allowing them to produce more cohesive experiences. And because apps only ask for the data they require and nothing more, performance of these experiences are optimized. The graph becomes the lasting home for product capabilities, unlocking richer experiences, new use cases, and business models by providing a discoverable and self-documenting API that gives easy access to all of your organization's capabilities. Meanwhile, service teams are decoupled from direct app requests, shortening their backlogs and allowing for more service innovation as they are freed from managing an ever-growing list of endpoints and consumers. The graph becomes the single source of truth within your organization, the point of collaboration for all teams, and ultimately, it becomes your product. So how do you go about building a unified graph? This is where federation fits in. It was designed to help you create a unified graph in a scalable and predictable way, allowing you to build a single graph API up from independently owned services, or subgraphs as we call them. Before we introduce the concept of federation, let's look at an example of how an organization might use GraphQL before introducing federation. In this example, there are a number of apps using Apollo client, Apollo's open source GraphQL client, to talk to an instance of Apollo server that orchestrates calling the underlying services shown on the right. This is often what the backend for front-end services we saw earlier might look like, with the Apollo server instance combining the responses of the various underlying services into something that makes more sense for the consuming apps. Federation builds on this model and introduces the concept of a gateway, also called a graph router, that composes a unified graph from multiple subgraph services that each implement a part of the graph. Requests come into the gateway from apps, which then runs each query through a query planner that decides which subgraphs will need to be called to fulfill the request and in what order. The subgraphs in turn then make calls to the underlying services. The big benefit of all this is that each subgraph is an independent service. Changes can be made to it independent of the other subgraphs, and Apollo Studio handles all the composition of a unified schema from the subgraph fragments. This allows you to take your API and break it into chunks to match your organizational structure or domains, or whatever else makes sense for your business, with each of these chunks being developed and maintained by domain experts. Federation is the glue that binds all of these independent chunks together into a unified whole. With federation, you are encouraged to split subgraphs by concern. This differs from other approaches, such as schema stitching, where subgraph boundaries are often delineated by types in the schema. On top of that, the graph router takes a declarative approach to composing subgraphs together, allowing it to handle query planning automatically, whereas other approaches create imperative pain points by requiring custom code to pull everything together. This composability really is the killer feature of a unified graph. On the back end, the move to cloud native has shown us the advantages of composability at the service level, and on the front end, libraries such as React or Vue enable composability via the use of components. This means that we have composability at both ends of the stack, with isolated components, loose coupling, and a declarative approach to assembling those components. But the traditional APIs that we use to connect our composable front ends and back ends are the opposite of all these things. And the more you layer them on top of each other, the more brittle they become. What we needed was composability at the API layer too. This was a GraphQL pipe dream for a long time, until the introduction of federation, that is, which enables this composability and replaces the brittle APIs we had before. Now that we've looked at federation in a bit more detail, let's have a look at a few simple examples to show how requests flow through a unified graph. First off, let's look at an example of a classic product page with many different UX elements, all powered by various underlying services and data sources. With GraphQL, it is possible to request data from all these sources in a single request as shown in the query on screen. This query asks for the user's ID along with a collection of product information, all within a single query. The app developer doesn't need to think about which services to call and how to link information on stock with product ratings. This is all hidden from them. Let's run this query through the graph. The query hits the graph router, which uses its query plan to figure out which subgraphs need to be called in order to fulfill the query and in which order. The highlighted components of the graph are the ones that are called in order to fulfill the query. The subgraphs then call the underlying services they need to get the data. Then the router combines all the responses together into a single response that is sent back to the app. The key point here is that the client is unaware of the actual service routing, but only sees the unified representation presented by the graph schema. Just as importantly, each of the subgraph types, such as product info or pricing or user, can be owned by different teams, while still presenting a unified model to all clients. It's worth noting that some organizations choose to federate their underlying services directly, meaning that the subgraphs and the services in this diagram become the same thing, but the above approach is a common first step. Moving on to another example, this time we have a desktop web product page, which displays pretty much the same information as the mobile app product screen. However, the extra screen real estate means we now have enough space to display customer reviews. So to include these reviews, we modify our query to include the review information we need as highlighted on screen. As before, the query flows through the graph router, which identifies the query contains a request for product reviews, and that an additional subgraph needs to be called as highlighted in yellow, which also lights up an additional underlying service. For the app developers, it's just a slightly richer query, but for the product managers and customers, the velocity and customer experience cohesion benefits are a game changer. No matter the app, whether it be a kiosk, a wearable device, or an email, it's the same story. The app only needs to change the query and the gateway will intelligently route the request to the right subgraphs and the right underlying services. In this example, our query is for an order. From a client perspective, all that changes is the contents inside the query. From a service perspective, everything just flows smoothly through the gateway to the subgraphs, and the services need to fulfill the query. Okay, now we've seen the value that the unified graph and federation can deliver to organizations, let's take a look at what the future has in store for Apollo. Well, we recently released version 2 of Federation. This was designed in collaboration with the community and involved a clean sheet implementation of the core composition and query planning engine at the heart of Federation. It builds on the success of the original with an improved shared ownership model, enhanced type merging, and cleaner syntax for a smoother developer experience. Federation continues to grow in popularity and recently surpassed over 1 million weekly downloads, with over 18,000 projects now using it. Contracts is an enterprise-only feature that allows graph operators to create tailored graphs for different audiences by applying filters to a single unified graph. This ultimately allows organizations to build and maintain a single graph infrastructure, whilst also offering customers with an API containing only a subset of their types and fields. This gives the ability to hide experimental features or create a public API or an API tailored around a specific client. Released on Friday the 13th of May, the team were brave with that one, Router is our new open source high-performance federation runtime written in Rust. This is an evolution of Apollo Gateway, which was written in Node.js, that offers much higher performance. Our benchmarks show that it's roughly 10 times faster than Gateway and with 10 times higher throughput. This step change in performance should make it much easier to run a unified data graph at scale and enable much faster APIs for everyone using Federation. Apollo Odyssey is our free-to-use learning platform. Anyone can use it to learn about GraphQL and earn an associate graph developer certification. We're adding more modules all the time, with a set of Federation modules coming shortly. If you're looking to learn a bit more about GraphQL, then I'd highly recommend you go check it out at apollographql.com/tutorials. And of course, we continue to invest in our other open source tooling. Both Apollo Client and Server have some major new releases coming up with some great collaboration going on in their repositories. Be sure to check them out on GitHub. I'd like to end this talk with a brief run-through of the Apollo platform and how it builds on the features of Federation, and how it takes this to the next level by providing the air traffic control you need to make building and operating your graph as simple as possible. The Apollo platform integrates directly in with your graph router and provides a number of essential elements to help you run and develop against your unified graph. From schema checks that help prevent changes to subgraphs breaking client apps, to observability tools that provide detailed metrics about the runtime performance of your graph, it is the go-to place for your graph consumers, devs, and admins. All of the infrastructure needed for running your graph runs in your own cloud and makes use of Apollo's open source tooling as shown at the top of the diagram on screen. The Apollo platform then connects into various components of your graph infrastructure and runs within the Apollo cloud. The Apollo cloud services can be split into two main parts, Apollo Studio and Apollo Registry. Let's simplify that diagram down a little and split out these two major parts of the platform and show how they integrate with your graph router. The graph router runs completely in your infrastructure and is the heart of your unified graph, optimizing query routing and connecting your applications to your underlying service capabilities, whilst hiding service complexity, endpoint configuration, and client orchestration. On the Apollo Cloud side, we have the Apollo Registry, which acts as a single source of truth for your schema, with all the subgraphs pushing any changes they make to the registry, which then runs schema checks to ensure there are no breaking changes. And then we have Apollo Studio, Apollo's web-based portal that provides observability and the governance of your graph and helps you build, validate, and secure it. Combined, Apollo Studio and Apollo Registry provide the control plane to manage the full graph lifecycle, change, check, and deploy. As mentioned before, the Apollo Registry is the single source of truth for all your schemas and all the underlying capabilities they represent and provide access to. In order to ensure the integrity of your graph is maintained, every time a subgraph service makes a change to its schema, this change is pushed to the Apollo Registry. A new supergraph is then validated and composed from the change subgraph and the other existing subgraphs, before being passed to your graph router to update its schema. This entire process happens every time a change is made to any subgraph and ensures there is always a single source of truth for your entire graph. One of the most important aspects of running a unified graph, and one of the key benefits of GraphQL in general, is the extra observability and insight you get. Usage and performance metrics are sent from your graph router to Apollo Studio, which uses these to provide detailed metrics on how consumers are interacting with your graph. By using client identifiers, you can see which clients and what versions of clients are accessing which parts of your graph. This makes lifecycle management much easier and helps identify which teams you might need to work with to move off an old or soon-to-be deprecated field within your graph. Consumers of your graph can use Studio's Schema Explorer to drill down through your graph and see reasons for deprecation or any other bit of information you provide. Comments from your schema are extracted and used to build a comprehensive set of API documentation that aids with discoverability. Studio uses performance metrics sent from your router to build up a detailed performance picture of your graph, showing how much your graph is being used, how fast it's responding, and where it's going wrong. Some of our other tooling integrates this performance information into both VS Code and Apollo Studio Explorer, giving developers insight into how quickly their queries should respond. With the introduction of a unified graph, your applications and services are completely decoupled, and your teams work together on a shared contract, not a specific endpoint or vision, but you still need collaboration, right? The combination of Apollo Studio and Registry provides a range of tools to help drive this collaboration. Apollo Studio contains a range of features to help drive collaboration, from its built-in IDE Explorer, which makes it easy to browse your schema and create shareable queries with a few clicks of the mouse, to the schema reference, which acts as the go-to source of documentation for your GraphQL API. You can even add contact information for services to make it easier for teams within your organization to interact. There are three aspects to the governance features within Apollo Studio. Firstly, schema checks are run on every subgraph push by Apollo Registry to validate that the changes being made don't contain any errors and are composable and won't break existing consumers of your API. It does this by using usage data for your graph and running all known operations against the new composed schema to ensure there are no breaking changes. The next aspect of governance is a flexible set of user permissions that dictate what level of access a user has information to within Studio, and what permissions they have to push changes to your graph. You can lock down the product version, for instance, to only allow certain users to push changes. And finally, we have change and audit logs to keep track of what has changed in your graph and who changed it. Let's take a quick look at schema checks in a bit more detail. There's nothing worse than making a change to an API, running your test suite and having every confidence that everything will work out fine, only to discover that there were some obscure client calls that weren't captured in tests. Panic ensues, changes are rolled back or fixed forward, and you end up slumping down on the sofa at night, swearing never to do that again. The good news with the Apollo platform is that Studio keeps track of all usage of your graph, and all changes you want to make to your schema are run against this usage data to ensure that those obscure client calls don't get missed. You can monitor all checks that have been run and drill down to identify whether operations might be broken or changed. Of course, sometimes you have to push breaking changes, and there is, of course, the facility to do this within the tooling. And with that brief overview of Apollo platform, we've reached the end of my talk. Hopefully you found it informative and it's given you a few things to think about. And if you've any questions, I'd be happy to answer them now.
Thanks a lot, Andy. We have some question here from the audience.
Yeah, not really a question, but feedback and a thank you, because we are already using GraphQL Apollo server on the Siemens.com with about 16 million requests each month. So it's a quite huge thing that enabled us to serve assets, content snippets, and so on. And we will definitely look into the studio thing and the federation thing as well, because that solves some problems that we have right now. So thanks for that. And I can highly encourage everybody to work with GraphQL. It's a weird thing in the beginning, but if you if you understand how it works, it's a cool thing. Yeah. So thanks for that.
You're more than welcome. I don't feel like I've done it myself, but from the company point of view. And having been in the same position where we I introduced GraphQL into RS components, I don't know, 3 or 4 years ago, that initial adoption, you start with it, it's like, oh, this is a bit strange. But then over time, give it like 6 months and you're like, okay, I can't do anything else now.
Okay, that's this. Hi. Hi. I have a question with regards to your slide set. So I wasn't really sure on which parts are now regarding open source. I mean, it's a really nice product, but which components of what you presented are under open source licenses?
Pretty much all of it. Obviously, the SaaS isn't. That's a commercial bolt-on. But Apollo Client, Apollo Server, Apollo Gateway, Apollo Federation, everything is open source. Obviously, if you use the open source versions, you then have to build all the tooling and the support mechanisms to enable you to use it, which is where the SaaS offering comes in. But you are anyone is more than capable of building out that tooling if needed. So yes, pretty much everything's open source.
Any other question? Yeah, have fun.
I have more of a question, like client side. How do you do nested pagination, or how would clients handle that? So I think when it's like a targeted application that knows exactly what nodes are paginated, you can just kind of hard code it. But if you want to have a generic client that doesn't know what elements will have pagination, would you have an answer to that, or do you just say application solves it?
There is an answer to that one, but I think it may use up the rest of the time. There are a number of different, like you can use for instance, there's a relay spec solution for pagination. There's a number of different approaches to pagination. My general advice is that when designing a schema, you have to bear in mind what can be paginated, what can't be paginated, and just come up with a standard approach to it. Whatever that approach happens to be, there are pros and cons to all the different pagination approaches in GraphQL. It's just picking the one that makes sense for you and for your users. That's the short answer. The long answer will take the next 10 minutes.
All right, thanks a lot.
Happy to talk about that another time, though. If you want to reach out on one of the things on screen, feel free, drop me a message on Twitter or something. We can talk about it further.
Thanks a lot.
We have another question here from the online audience. How would you compare GraphQL with its simple queries but required GraphQL schema creations registry to Sparkle with more complex queries but no intermediate schemas?
That would involve me Googling what Sparkle is. Hard to answer that one without knowing what I'm comparing it against.
Do you?
Sorry, maybe this is like a, feel free to refuse to answer, it's like maybe a too honest question is, I mean, we have an ongoing effort in Siemens to have like an API platform and so, and what's the catch? I mean, we have been, let's say, confronted with GraphQL, with GitLab itself, GitLab provides a GraphQL endpoint. They never end up replacing it, though, to my knowledge, it was announced several times, GraphQL is the future, but they still keep the REST base, and that's the obvious kind of alternative. Okay, how does it compare to REST, and where's the catch, or where's the difficulties compared to the standard approach?
I think there's a few answers to that. One, I don't think I did mention, but my history is very much as a front-end developer. I've spent most of my career being in the front end, and I've transitioned into GraphQL and the API side of things later on, but now obviously 100% focus on it. And I think what's been happening over the past 10 years in the industry is that the back end has found the joys of microservices, and it's created this dream of these microservices and all these different APIs, and they've pushed the complexity of handling all of those APIs onto the clients. That's made them increasingly more challenging to build and much harder to actually maintain and run. So I think REST works from a back end point of view, but from a front end point of view, it just doesn't work because you have all this orchestration complexity. So GraphQL helps solve that from the front end point of view, but also then helps satisfy some of the problems that the back end has by actually decoupling themselves from the front ends. You get a much simpler kind of like a collaboration model. And I think that's the biggest catch with GraphQL as a whole, is that you have to have collaboration. And generally speaking, it's not something that engineering organizations are amazing at when it comes to working across, say, front ends and back ends or domains or whatever else. Everyone's objectivized to think about their thing. Dan Berner, a colleague of mine, refers to this as tragedy of commons, where you effectively have, everyone's incentivized for like doing the thing they're incentivized to do, like saying getting water out of a well, they'll just keep getting water out because that's what they need. They never think about how much water they're using for everyone else. Whereas if you actually then think about things strategic, kind of like thinking about everyone's sense, you're gonna ration that water across the entire community, not just about yourself. And I think this is very true when it comes to APIs and the dream of microservices, is that a microservice, generally speaking, is only concerned about itself and its API. It's not concerned about how it combines it. So is GraphQL a silver bullet? I don't think anything's a silver bullet. It's a big step in the right direction for creating a collaborative environment inside an organization that serves out a unified API that clients can use and that doesn't put too much load onto back-end teams. I often think the biggest challenge of adopting GraphQL at like an enterprise scale, so in that unified graph kind of model, is more about the organizational challenges and the people side of it, more so than the actual technical. That was a very long-winded answer. Hopefully it answered the question.
So we have another question here.
A quick question about the federation. I was wondering, is this a fully recursive thing, so all the subgraphs can again be routers with its own subgraphs, or is this always a two-layer thing?
Technically, it all depends how you look at it. So, as things stand today, federation only goes one layer deep. In that, there's certain things that need to be added to a subgraph schema to then inform the gateway, the top level, how to route things around the place. There's not this recursive, you can go from a gateway to a gateway to a gateway to a gateway. But that's not to say that you can't use like a GraphQL aggregator. You can aggregate services inside subgraphs, which then aggregate other things. So you wouldn't be able to build like a federated graph of federated graphs, but you could have a federated graph of subgraphs that called a federated graph. If that makes sense.
Okay, thanks. I think I will.
I have also a question. Companies or organizations that are using GraphQL at scale, are they GraphQL only now, or it's always something you always need anyway, have the REST APIs, and it's on top you have a GraphQL. You can't survive without both, let's say.
Well, I can speak from personal experience here. As I mentioned earlier in the talk, I used to work for RS Components. And part of the strategy that we were working on, I've left a year and a bit ago. I have no idea if they're still following it. But the strategy we were working on was to make everything graph native by default. But the reality of any situation is that there are going to be older systems, whether internal or external, or consumers that just don't talk graph or be able to understand it. They know REST and they only know REST. So the strategy we were taking there was to actually put REST endpoints in front of GraphQL. So you make a REST request, it hit an endpoint, it would then fire a fixed query out a unified data graph, which would then get all its data and return it. So effectively, the unified graph became the only place to get data from the API layer. But then the REST endpoint just became another client of that. That gave us all the benefits and be able to like only worry about one lot of code for fetching all the data, and also ensure that we had that prevention of breaking changes at the actual data graph layer. So if it's quite easy in like an enterprise thing to make a tiny little change somewhere, and then before you know it, 6 REST endpoints that you've never heard about are broken. Because all that was being tracked in the data graph, it meant that we could never do that unknowingly. It would just happen. If it happened, it would be an intentional break as opposed to an accidental one. As to whether teams will go, organizations will go all GraphQL or whatever. Some might, and I do know of some that are 100% GraphQL. But I think in organizations with a lot of history, that's a polite way of putting it, there's always going to be computing technologies and older systems that you can't upgrade to use the more newer things.
Thanks a lot. We have another question.
One last question.
So, and this might be a bit of a unfriendly seeming question, but I promise you it's not. So what I see, and I'm an ops guy, is that it seems a bit like if you're trying to mitigate badly written backends by introducing another layer that you have to operate on top of it, and that basically its job is to mitigate badly written backend APIs. So by making tracing and profiling of issues harder because you have an intermediary layer that's much more complex than a traditional API gateway that pulls into your SaaS software, that's really hard to debug in the end. So what do you think about this really big blob of added complexity to basically mitigate badly written backend APIs and people not being able to read, front-end people not being able to read Swagger API definitions?
There's a few things in that. One, yes, it does add additional layers, but this is my belief before I joined Apollo, so it's not just an Apollo thing. My belief is that concept of a data layer was missing in architectures, and enterprise architectures. The complexity of getting data from wherever you need to get data from. Something has to do it somewhere. And we've, for many, many years in the industry, just been trying to ignore this problem and pushing it to wherever it could be handled. So by explicitly calling out the need that there is something that has to handle this data orchestration, I think is a positive step for organizations, in that they now know that, yes, they've got all this complexity in the back and they've got all these clients in the front, but they have this one place where it can all be handled. So it makes actual routing much easier to follow, and also presents a number of opportunities. I'll use RS components as an example again. We introduced like caching at the data graph layer, which actually then reduced the number of calls going to the services behind and reduced load on slower systems. So it allowed us to put a single layer in place where we knew we could control things, and obviously via event-driven architectures or various other things, we have ways of invalidating that cache so that it actually speeds up the entire process. Now, the bit about badly written back-end APIs, I think that's the reality of most organizations, whether it's newly badly written APIs or something that's been there for 10 years that you can't change because no one knows how to change the code. It makes sense to do that somewhere centrally as opposed to having to spread the conversion of this nasty API into something that makes sense across like 20 different consuming apps. So there's positives to it. I will agree that adding in an extra layer isn't ideal. But I think if organizations adopt a microservices architecture, it's unavoidable in the long run. Something somewhere has to handle the complexity of orchestration. And for me, GraphQL is the natural thing because it solves lots of other ancillary problems.
We have another question here. What technology do graph native resolvers use? Not just REST APIs?
Whatever you want. So there are I think I'm trying to think of a tech stack there isn't a GraphQL server for, but there are lots and lots and lots of different technologies available. So off the top of my head, I know there's some for Go, there's some for Rust, there's some for .NET, there's loads for Java, Scala, Kotlin, etc., etc., etc. I think that's where the benefit of open source has really kicked in, because obviously Facebook open source GraphQL initially, it got widespread adoption. Yes, Meteor/Apollo jumped on it quite early. They established quite a well-known position in the market, but then lots of other companies did too. And then a lot of the other innovation that's come out of GraphQL since has all been open sourced. Federation is an open source spec, and anyone can implement it in their own frameworks. Best example of that recently, Netflix with their open sourcing of DGS, which is Netflix work quite closely with Apollo. They're part of the Federation working group, so they contributed quite a bit to the new Federation 2, all part of this kind of like collaborative open source kind of thing. So the answer to the question, they can be written in whatever you can find something that supports it, which is probably most languages over the past 20 years. Go back to COBOL, you might be struggling, but you know.
All you can code, you can do GraphQL. Nice.
Yeah.
Thank you so much, Andy. Pretty sure we will see more GraphQL-like thingies in the next few weeks or months. And yeah, let's keep in touch, and thanks a lot.